So as a small example, if we take the example of a D flip-flop, suppose we give the input enable and output enable control signals to the D flip-flop. Then we have to ensure that a little after this D gets high, we have to also assert this input enable line so that the input D reaches this D input of the flip-flop. And then in order to get the output, we have to assert this output enable line. Now obviously, if you want to see how this input D is reflected at the output, you have to ensure that the output enable is asserted a little after the input enable is asserted. Why? Because we are bounded by the propagation delay of this circuit. The signal takes some time to propagate through this circuit before it is available over here. So we have to take all these minute details into consideration when we are modeling the hardware. So what are the approaches by which we can model the hardware? Two popular schools of thought is there. One is that you start with the whole design, split it into modules and submodules, ultimately arriving at the elementary level modules. That is what we mean by the top down approach. So once you arrive at the elementary level modules, you implement the elementary level modules and then integrate those modules together into a solution for the whole. So to see it graphically, we start with the top level module, then split it into 4 submodules, then again split each of the submodules into further sub-submodules and so on. So I mean, I have shown it for 3 levels. It doesn't mean that you just do the design in 3 levels. You can go on iterating, ultimately arriving at the elementary level modules. The other school of thought is the bottom-up approach, in which you start your design with the design of a single transistor or a single gate and then integrate the design, go on adding components to it, ultimately getting the whole design. So now which one is better, top down or bottom up? In top down, the advantage is that we can start analyzing the circuit from a functional perspective, split it into modules and submodules, assigning separate tasks to the separate modules, and gradually go on translating our behavioral notions into structural notions about the circuit. While it leads to rapid development of the system, on the other hand, you lose considerably in terms of the accuracy in the behavior of the circuit. Because when you are focusing more about the functional perspective of the circuit, you are less focusing on the accuracy of producing results or timing accuracy in the behavior of the circuit. And so you in the final design you lose considerably in terms of accuracy in the behavior of the circuit. On the other hand, in case of bottom up design, while you accurately design the circuit, because you start with a single MOS transistor, check whether the behavior of the transistor is correct or not, and you go on incrementally adding components to it, ultimately arriving at the whole circuit. So at each and every step, you become ensured or confident about the behavior of the circuit. So you gain in terms of accuracy of the circuit. On the other hand, the design cycle time becomes too large. So that's why we typically go by the bottom up approach when it comes to analog design. And in fact, in practical cases where we both need a short design cycle time as well as a reasonably accurate design, we use a combination of both the top down as well as bottom up approaches. Okay. To take the example of a full adder, that means the 4-bit triple carry adder, you can visualize the 4-bit triple carry adder as a collection of 4 single bit full adders, and each full adder as a collection of XOR, AND and OR gates. Now, when you are designing the circuit, you may start from analyzing the 4-bit triple carry adder and then arrive at the level of XOR, AND and OR gates, or you can go by the reverse procedure. That means you can go by both, either the top down or by the bottom up philosophy. But in essence, when we want both speed and accuracy together, we use a combination of the top down as well as bottom up philosophy. Okay. So this is what I said, that while top down approach yields us a speed a speed in terms of the design cycle time, we lose in terms of accuracy. On the other hand, in case of bottom up approach, we gain in terms of accuracy in the behavior of the circuit, but badly lose in terms of the design cycle time. So that's why we, in practical design problems, we use a combination of both the top down and bottom up approaches. So you start with the design of AND, OR and XOR gates. You design the AND, OR and XOR gates, then use the AND, OR and XOR gates to design the full adder. Okay, and then you integrate the full adders into the design of the 4-bit triple carry adder. Now there is a interesting thing in this, that if you go by the top down approach, then the dimensions of all these XOR, AND and OR gates will be the same, because you are looking at each of these XOR, AND and OR gates identically. But if you think it very deeply, then the loading effects of the different transistors in the design, in which are used for implementing these XOR and OR gates, are different. So if this is the first stage full adder and this is the final stage full adder, then this full adder will be most loaded at its output, because it is driving the next 3 stages. On the other hand, the last stage full adder will be loaded the least, because it is not driving any more stage. Now if you want to ensure that the sum outputs of all the 4 bits are available at the same instant of time, then you have to do accurate impedance matching calculations to ensure that all the 4 sum outputs are available at the same instant of time. And in order to do this impedance matching, you have to accurately tune the aspect ratios of the different transistors which you are using to implement your design. So such fine details can be taken up if you go by the bottom up approach and not the top down approach. So people nowadays are more fond of the top down approach because they can turn out things within a reasonable span of time. On the other hand, with the top down approach, lots of faults get excavated within a short span of time, and within some time you can realize that your entire design is faulty. You have not taken into consideration various fine details. So one of the effect of this top down approach is that if you consider today's technology, in today's technology we buy things which last for a small period of time. I mean, today if you buy laptops, those laptops do not last for more than 3 or 4 years. After 3 or 4 years, you are so much frustrated with its performance that you will throw it away. This was not the scenario some 10 years back when you would have paid some 1.5 lakhs or so to buy a laptop. Now laptops are available at 25,000 or even less. I think even 15,000, or with 15,000 or 18,000 also you can get a laptop, right? If I am not wrong, with 15,000 or 18,000 rupees you can get a laptop. This was not the scenario some 10 years back when you need to pay some 1.5 lakhs or so to buy a laptop. So that is how because of this rapid prototyping and all that, technology is becoming cheaper and cheaper because you can turn out more number of things within a short span of time. So that goes by the law of demand of economics. On the other hand, we are losing in terms of the quality. So there should be a good optimization between the time to prototype and time to market versus the quality of design. So design really exists at different levels of abstraction. As you go on developing your system, you have to consider the different levels of abstraction. We start with a system level description, which means we visualize the system as a whole without referring to its components. We are only bothered about the behavior of the circuit, and then translate our notion into an algorithm depicting accurately the behavior of the system. And gradually this algorithm is translated into the architecture of the circuit, and after that the architecture is translated into the data transfer between the registers, which means we exist at the RT level or register transfer level. And finally these register transfer level descriptions are translated into the gate level descriptions, which is similar to what you have learnt in your digital logic. And below the gate level exists the transistor level, which means you visualize each and every gate as an interconnection of transistors. But at each step we really need to verify whether the circuit specifications are being met or not. So at each step we have to check whether the initial specifications of the circuit has been met or not. And therein comes the notion of all these computer aided design tools and all these circuit analysis softwares. So coming to the algorithmic and system level design, it is basically a formal description in some hardware description language. We depict the behavior of the system in terms of some language which we call the hardware description language, that describes the that models the circuit basically. And then we use some programs called simulators to find out the error in the specification and then retune the specification to meet the desired behavior. Once we are okay with the behavior of the circuit based on the algorithmic description, we use synthesis tools to generate a description about interconnection of logic gates to depict the behavior and to depict the structure of the circuit. So this description of interconnection of gates, which we are calling a net list, a net is basically a wire connecting the components. So if you want to have an idea of net list, let us assume a circuit consists of these three modules M1, M2 and M3. And these three wires are there, N1, N2 and N3. Okay. Now, as I said that when we want to communicate our ideas about this circuit to the computing system, we have to use the notion of some text to convey our ideas about the circuit to the computing system. So how to do that? We can visualize this system as a collection of these three modules M1, M2, M3 and three nets N1, N2, N3. So we can think of it like this, that module M1 is connected to nets N1 and N2, module M2 is connected to nets N1, N3 and module M3 is connected to nets N2, N3. So we can have a list like this which depicts the list of modules and what are the nets connected to the individual modules. So this is one way of depicting the structure of the circuit. The other way can be, I can write it as a list of three nets. So N1 is connected to modules M1, M2. This N2 is connected to M1, M2, M3 and N3 is connected to M2 and M3. In either way, we are giving the description about the same circuit, in which either we list up the modules and show the nets connected to the individual modules, which establishes the connectivity between the modules, or we find out the set of nets and find out the set of modules connected to the individual nets. So this list of modules or nets that depicts the interconnection of the components in a circuit, that is called a net list. In the former case, in which we list up the modules and then find out the nets connected to the individual modules, that type of netlist is called a module oriented netlist. And the latter case, when we list up the nets and find out the modules connected to the individual nets, that type of netlist is called a net oriented netlist. So over here, if you consider a 2-to-1 multiplexer, we can depict the set of inputs, the set of outputs, but there are also a set of wires which are not visible from outside, like the A underscore cell, B underscore cell and S underscore bar, that we also need to define. Now if you visualize the circuit as a collection of these two AND gates, one OR gate and one NOT gate, and depict the nets connected to these individual modules, then it will be a netlist. On the other hand, you can also specify the set of nets, that is A, S, B, S underscore bar, A underscore cell, B underscore cell, W, and specify the modules connected to them. So when we are conveying our ideas about the circuit, in either way we can convey. However, the more popular one is that normally we look at the components with which we build a circuit. That's why we use a module oriented netlist. Below the gate level comes the transistor level, at which we express each gate as an interconnection of transistors. In fact, in earlier days, when people were not too much bothered about optimizing the circuits, people would directly translate each gate into an interconnection of transistors without applying any optimization in that step. But now we are in an age at which we really need to find out how we can further optimize the circuit at the transistor level. We need to cut short the number of transistors to satisfy the requirements with a lesser number of transistors, which means a lesser circuit area, and therefore lots of optimizations are done at the transistor level. So what are the things we really need to take care at the transistor level? We need to take care about the switching behavior of the circuit. We really need to take care of the timing behavior of the circuit, which means we have to ensure that the appropriate signal reaches the appropriate transistors at appropriate instance of time. And for analyzing these circuits, we have to use the notion of models of various components and devices that we use in the circuit. For example, when you use a MOSFET in a circuit, you have to describe a spice model of the MOSFET to express the behavior of the transistor in terms of simpler components. Below the transistor level comes the layout level design, in which the problem becomes more geometry oriented rather than physics oriented. So if you look at the entire design flow process, our notion about the system initially existed at the algorithmic level, in which we depicted the behavior of the circuit in terms of some functional description or algorithms, and then those algorithms evolved into some Boolean equations expressing the interconnection of gates. And further down, when you come to the transistor level, you have to write equations and analyze the behavior of the circuit. So you have to use the IV equations for the different devices with which your circuit is made up of, and then analyze the behavior of the circuits, find out the node voltages, branch currents, and so on. So that is what we really mean by analyzing the physics of behavior of the circuit. So it starts with algorithmic level description, then Boolean equations, then analyzing the physics of the circuit, and below the physics of the circuit you are basically analyzing the geometry of the circuit. So at each level you basically take help of your basic concepts of mathematics or physics to analyze the behavior of the circuit. So this layout design process is a multi-step process which starts with partitioning the circuit into certain sub-circuits and analyzing each sub-circuit, which is what we mean by circuit partitioning, so that the circuit analysis and design process becomes a problem of manageable size. And then we come to finding out in what part of the chip will place the individual components. That is basically the floor planning phase. So this is again a multi-step process. So first we find out the approximate location of the components where we place, and then we find out the exact size of the components. So if you want to depict it pictorially, say this is the circuit we need to lay out. So you first partition it into individual modules. Now you find out the location of these individual components on the chip. So whether you can go for this type of design or whether you will go for this type of design or so on. In fact, this basically refers to the type of algorithm that we follow for floor planning, that is rectangular slicing floor plan. We divide the chip area into rectangular slices and find out which slice is amicable for what component and so on. After the floor planning is done, we find out the exact location and exact size of the individual components in the placement phase. Till the placement phase, we are concerned with the individual components only. We are not concerned about the interconnections of the components. That comes in the routing phase. So this routing phase is again a two-step process. In the first phase, we find out the approximate pathways through which we'll lay down the wires, and in the second step we find out the exact pathways of the wires between the components. Because this has been done as a two-step process, because we in the layout design, if the layout is not properly designed, then the effects of the parasitic resistances and capacitances of the metallic interconnects dominates and considerably affects the behavior of the circuit. So while you are designing the circuit, you may be okay with the schematic, you may be okay with the behavior of the circuit from its transistor level schematic, but once you design the layout, you may be surprised to see that the behavior of the circuit has entirely changed. So when a schematic of a circuit is analyzed, the effects of this parasitic in resistances and capacitances of the interconnects are not taken into consideration. But when it comes to the layout design, you have to take into consideration the effects of this parasitic resistances and capacitances of the interconnects, and therefore if you do the post layout simulation, you will find that your results are different. However, our requirement is that the results should correspond to the initial simulation results over a certain error spectrum, and that's why after we do the layout design, after we do the post layout simulation verification, we check whether the initial schematic corresponds to the layout or not. That is what we mean by layout versus schematic verification, or LVS. So there are design rule checkers for checking the mask geometries, and we also use circuit extractors for extracting the final circuit from the layout, and then we simulate the circuit for verifying the functionality. So once you design the layout, you use the DRC to see whether any design rules have been violated or not, and then after the circuit has been designed, you do the LVS to check the whether the layout being designed corresponds to the initial schematic or not. So by now we understand that the importance of simulation in the VLSI design flow, and we understand that simulation programs are immensely essential to verify the functionality and timing behavior of the chip. And in fact, 70% of the total effort being spent in bringing out a chip is spent at this design level only, and only 30% comes in the fabrication and post fabrication verification. So there's a popular joke that you design your circuit, you fabricate, and then you test the circuit, and then you find errors in it. What will you do? You are at vain. You have designed a circuit with millions and millions of transistors, you have not checked any design flaw in it, you have spent so much for fabricating the circuit, and after fabrication you have found a flaw in it. You are totally gone. So for this type of giant circuits, you really need to take care whether the design is correct or not at each step of the design process. So your design has to be spiced before it is cooked. You have to add masala to it, which in terms of simulation, and spiced well and many times before each stage of the design by simulation. So this is what we really mean by analysis, and SPICE is a simulation program and SPICE is an analysis tool. So at each step of the design process, you have to check whether your requirements have been met or not.